to be. And then this one is at 3.7. Now it's going to be 3 and 2.65. Why? So when I connect these, I connect them, but then that's the last one I have, right? So do I just wing it and hope for the best after that? Just draw an arm till the end and just totally wing it? Or do I actually lose marks to do that? You can go a little bit past it, but then you throw an arrow on it because you have no more graph to actually sketch the rest for this one. And I go with this one and I sketch it. So like just what I said, the reason why those x-intercepts are so important is because that's why graph's going to start. So that's what we're going to use for our domain, right? So our domain is a square root function. Our domain is going to be x such that the rest of the graph, that red graph that exists, is less than negative 2.79 or greater than 1.79, right? So we write it as x is less than, is it equal to? Can it equal over y0 on these ones? Can we take the square root of 0? Yeah, that's an invariant point. That's a point that will exist. So the square root of 0 is 0, right? You know, it gets mixed up with the other radicals. So it's less than or equal to negative 2.79, or x is greater than or equal to 1.79, and then x is down on the real. In set notation, it looks a little funkier. We go negative infinity to negative 2.79 square bracket, and or is union in set notation. It looks like a U. That means or. And is the opposite way. And then we're going from 1.79 equal to infinity. Now what's my range? Range this one. 90-year-old trapped in a 39-year-old body. The range of the red one. You can do this. I believe in you. Yeah, greater than. Yeah. Yeah. There we go. We got there. Anna was supporting you. She's throwing you the knowledge. With her mind magic. Yeah. Okay. So I want to show you something. So if I give you certain graphs, your range won't always be greater than or equal to 0, right? This one is concave up, so it is going to be greater than or equal to 0. And if I gave you like a linear graph, say it was like this part would go away. And then this would stay, this would stay, this would go up here, this would drop down, and it would do something like that, right? But if I gave you a graph like this instead, would it be YER? Let's say this is 9. Would it be YER? No. This would go away. This would go away, where x equals 0 and 1 would stay, right? 0.5 would just go a little above. And 9 would drop down to where? That's not at all drawn to scale. To 3. And it would go like this. So what would my range be for this one? Between what? 0 and 3. What if I give you something like this? None of it goes away, right? The whole parabola would be above or something like that. None of it goes away. The 4 would drop to a what? Would drop to a 2. And then these would drop down as well. Would there be any invariant points? No, there's no y equals 0, no y equals 1. right? So sometimes they do this as well, just so you know. Sometimes they'll go like this, they'll ask you for the number of invariant points between y equals f of x and y equals square root f of x. Okay? So say I give you this. How many invariant points are there on this one? 1, 2, 3, 4. Right? So that one would have, it's like one of those numeric responses they give you. We're going to have 4. What about this one? How many does this have? 1. Right? What about this? How many would you have? 1, 2, 3, 4. What about this one? 0. There's no place to cross a 0 and 1. There's no there. You need to know that when you see this, invariant points lie at y equals 1 and y equals 0. Why? Not because you memorized, but because xy becomes x comma root y. And root y stays the same when y is 0 and 1. Root 4 becomes 2, root 9 becomes 3, root 7 becomes 2 plus 4, right? It all changes except for 0 stays 0, 1 stays 1. All right, we have a new wow. 11. We're in grade top. So we talked about rationals in grade 11, rational equations. When you went to talk about rational equations, what did your teacher make you do first before you got into the question? Rational, what's the friend say? On the paper. So the equation. And how the variable in the numerator and variable in the denominator. How the number of the numerator and variable in the denominator. So these equations. But last year we did operations. You did addition, subtraction, multiplication, division. This year we're just looking at the graphs of them. Literally, that's it. Look at the graphs of them, transforming the graphs of them. So when your teacher gave you these, they said before we add, before we subtract, before we multiply, before we divide, before we simplify, we have to do what? State? Yeah, it's part of your soul. You didn't even mean to say that you stopped yourself. Yes, it's PDs. So state the non-permissible values. And this is the first time we ever really had a non-permissible values. Because it's the first time we were given a fraction with the variable we denominator. Other than that, we were given a fraction with a quarter, 3 quarters, 1/7. None of those have non-permissible values because there's no variable in the denominator. What's our rule? Our rule is that we can't divide by 0. So our rule is that our denominator cannot be 0. So if we get a variable in our denominator, we have to say what those x values can't be, because if we have them, it would make our denominator equal 0, which is a problem. So if we look at, let's look at one that's simpler first. So let's look at this one here. -2 over x minus 4 minus 6. What would be our problem x that would cause our denominator to be 0? If x was 4, we would be in trouble, right? Type this one into your calculator. If you have the old calculators, keep in mind that you have to type in, oh, I was going to grab, put this on my other computer so I could show you the calculator. Oops. If you have this in an old calculator, you have to show that this is a fraction first. You have to open a bracket, -2 divided by, and you want to divide by the whole x minus 4. So it has to go in brackets, close bracket, -6, into your y equals 2 on the left side. So I'm going to actually tell you something first, because a lot of you have your window changed to what I had before. So go second window. Remember I made you change your table set last time? Go second window and change your change in table to 1. Change it back to 1. So if you go second window, you change that change in table back to 1 if you haven't already. If not, your table's going over by 1, probably 4 or something. So alpha y equals enter. If you have the new calculators, you should be using alpha y equals enter because it's just easier to type it, right? It looks just like it. If you have the old ones, you have to bracket. This calculator will do brackets first. Did you calculate one thing for sure that calculator line or a gap in the graph at x equals 4? Do you see like an open space where the graph is curving on both sides of 4, but it's not going through 4? You see how it's doing that? It's getting close to 4 and then it's like shoot down, or it's getting close to 4 and it's going to shoot up, right? Like it's not going through it. If you have the old TI-84s, I just want you to know, or 83s, I just want you to know that your calculator believes everything is continuous, which it's not. This is not a continuous graph. So what your calculators will do is they'll go, instead of curving by the asymptote and then like curving on the asymptote, they do this. It's continuous. I need to connect them. And then it connects them. And it draws something like this. This doesn't actually exist. Your calculator just believes things are continuous. And then they got smart after they made yours and reprogrammed it to not make everything continuous, because not all graphs are continuous. Okay? So if you have a TI-83 that literally is drawing an asymptote where your asymptote is, just keep that in mind. Okay? All right. So let's go back here. The asymptote is where the graph doesn't exist, right? It's that dashed line where the graph doesn't exist. We have horizontal asymptote on an exponential graph at x equals or y equals 0. We had on a log graph, we have a vertical asymptote at x equals 0, correct? Now, bless you, we have an asymptote at x equals 4. That's a vertical one, right? Because x equals our vertical asymptote, y equals our horizontal line, horizontal asymptote. And why is it at x equals 4? Because the graph can't exist there. Because if it did exist there, what would our denominator be equal to? 0. So actually, circling back to grade 11, your vertical asymptotes exist where your non-permissible values exist. Unless the factor cancels off. Then it's the point of discontinuity, which we're going to talk about tomorrow. They're my favorite. All right. So here I have a 2x minus 1 on the bottom. Do you look at this one? And the 2x minus 1 cancel off from the top. Now these are sewn together by titanium. Remember how we talked about that? So what did we do? How did we solve last year? Well, this one we could say is 4. What did we do? We said 2x minus 1 can't equal 0 when it was a non-permissible value, right? But our asymptote is actually where it exists. So instead of saying can't equals, which is what you do with non-permissible values, your vertical asymptote is at 2x minus 1 equals. Wherever that equals 0 is where my asymptote is going to be. So that's why I put an equal. Then I just solve it out. Add 1. 2x equals 1. And x equals a half. Everyone type this one in. 3 divided by 2x minus 1. Remember, if you have the old calculators, that 2x minus 1 is still bracket. Okay. So do you see at x equals a half between 0 and 1? There's a gap, right? It's circling. What's the problem with this non-permissible value? This 2x squared minus 5x minus 3. What do we have to do? Decomp. Ah, factoring. It's back again because it never leaves. It's like that ex-girlfriend that just can't get to go away. You know? So many decomps. Okay. What times what equals negative 6? What plus what equals negative 5? What do we get? Negative 6 and 1. So we get 2x squared minus 6x plus 1x minus 3 group. Take out a 2x, left with x minus 3. Don't have to take anything out of that one, so I take out a plus 1. And I get 2x plus 1, x minus 3. So this equation actually looks like this. Y equals 4 over 2x plus 1, x minus 3. Do either of those factors cancel with the numerator? No. So how many vertical asymptotes am I going to get this time, actually? Yeah. Under 2? 2. Because there's 2 separate, completely different ones, right? So what do? If 2x plus 1 became 0, 0 times x minus 3 cancels. If x minus 3 became 0, 2x plus 1 times 0 cancels, right? So both of those brackets can't be 0. So where are asymptotes going to exist? When 2x plus 1 equals 0, and when x minus 3 equals 0. So this one's going to be x equals negative a half, and this one's going to be x equals 3. Type this one in. You can type in the original if you'd like, just so that you can see what a graph of 2 asymptotes is. This one, we have negative 2x plus 3 equals 0. So negative 2x equals negative 3, and then x equals 3 halves. That would be 1.5. And then this one, we have 4x plus 3 equals 0. 4x equals negative 3, and x equals negative 3 over 4. That's where the vertical asymptote exists, right? But where the graph does not exist. Where the asymptote is where the graph is not. So if you can get the vertical asymptote, you have your domain. If you look at your graph, your domain exists everywhere but there. So when we have graphs like this, say we have an asymptote here and an asymptote here, and we have a graph here and we have a graph here, your graph actually exists at every x value but your asymptote, doesn't it? Like it's the only x value that doesn't exist. So in set notation, domain's really easy. Once you have the asymptote. If you can't get the asymptote, then you're in trouble. But the domain here is going to be x such that x can't equal 1/2, which is true. X can't equal 1/2, but equals everywhere else, right? So how do we represent that in domain? We say x such that x can't equal 1/2, but x is an element of the real. So x is everywhere but there. So literally, instead of saying it's negative infinity to half, round bracket, half to infinity, which is what you have to do in set notation, you have to go negative infinity to a half, round bracket, or a half to infinity. We're just saying x can equal 1/2, but it equals all the other real numbers. So we'll do set notation for the rest. This one is going to be x such that x can't equal 4. X an element of the real. This one, when you have 2, you just get a comma. X such that x can't equal negative a half, comma 3. X an element of the real. And this one is going to be x such that x can't equal 3 halves. X an element of the real. And then this one's x such that x can't equal negative 3/4. X an element. Then we're going to do horizontal asymptotes. Horizontal asymptotes are based off of rules. They're actually based off of limits as you approach infinity or negative infinity in calculus, but you don't have that, it's off of rules. So, n represents numerator, d represents denominator, and we're looking at the numerator degree and denominator degree. Numerator degree, denominator degree, numerator degree, denominator degree. And these rules only work with full fractions. So full numerator over full denominator. We've talked about this before because you can't do proofs that you can't flip them unless you have full fractions, right? if it's division. You can't multiply unless you have full fractions. Full fractions just means full numerator over full denominator. So the second one is the only one that doesn't have that, right? Second one does not have a full fraction. So we're going to have to do that in a different way. But first, third, fourth, and fifth do. So we're going to look at the degrees of the numerators and degrees of the denominators. This one doesn't have an x, the numerator, right? So we can write it as x to the what? X to the 0. Because what is x to the 0, just? 1. Anything to the power of 0 is 1. Remember, taking to the power of 0 is 1. Now this one is x to the 1, right? So my numerator is a lesser degree than my denominator. Is that true? When that happens, numerator is a lesser degree than the denominator, it's always y equals 0. So it's going to, your asymptote is going to be on the x-axis, right? We're skipping number 2 because number 2 is not a full fraction. Those rules do not work with number 2. Number 2, you cannot use those rules. Okay? Number 2 and number 2. Good. What's the numerator degree on this one, the third one? X to the 0 on this one's degree? 2. So once again, my numerator is a lesser degree than my denominator. So what is my horizontal asymptote? Y equals 0 again. We come to a pattern. The next one is degree what? The degree of the numerator is 1. The degree of the denominator is 1. Ruh-roh. Stay the same. When they're the same degree, when the numerator equals the denominator, you end up getting a fraction of your leading coefficients. Unless it can cancel off. So let's look here. What we do is we take a fraction of their leading coefficients. So it's the numbers that are in front. So I have a 3 here and a negative 2 are both in front of the x to the 1. So it's going to be y equals 3 over negative 2, which they could write as negative 3 over 2. Or they could write it as negative 3 over 2. Same thing, right? That negative sign can move as long as there's only one negative. Trick question. What's number 5? Degree what over degree what? And I'll always bold where they are, because then I don't mess up and pick the wrong numbers. Degree 1 is here. Degree 1 is here. So their leading coefficients are not 2 over 4. What's their leading coefficients? Negative 5. Second one is not in full fraction over full fraction. I can't use those rules, right? Can everyone in their calculator type in y equals 1 over x? This is why I was going to grab this to more calculator. You have something that looks like that in front of your faces, right? That's the y equals 1 over x graph. Now, is this the most accurate graph you've ever seen? Like, would this get you a 10 out of 10 on a test? I didn't even plot a point. It would not. It might get me 0.5 because I drew the asymptotes. That's about it. You draw the asymptotes as dashed lines, right? Because that shows that the graph is there, but like that there's a dashed line, there's an asymptote there. That's how you represent an asymptote. Now, that last question was like this. Y equals negative 2, x minus 4 minus 6. My parent function, so my original, is y equals 1 over x. That's transformation notation, guys. You see it? What the heck would move? What the heck would move my horizontal asymptote? Like this. Only that there's a horizontal asymptote, just like exponentials, is a vertical translation. What is my vertical translation on this one? 6 units down. So this one's going to be at y equals 6. Now, I have a vertical asymptote at x equals 0. What's moving this? Horizontal translation, which is 4 to the right, which reaffirms that I was right. But I can always use my non-principal values to get that. Yeah. I'm an idiot. It's supposed to be minus 6. It's 6 down, so it should be minus 6. Good catch. So is the range hard if I can find the y's? No, it's the exact same as what we just did, except it's with y. So let's do this. Y such that y can equal everything but 0. So y can't equal 0, but it can equal everything else. So I represent it. And this one. Y such that y can't equal negative 6, but it can equal everything else. And then y such that y can't equal 0, but it can equal everything else. And then this one, y such that y can equal negative 3/2, so 3 to negative 2. I like the top better out of the numerator. And then this one here is going to be y such that y can equal the negative sign in the numerator, so it's better at the top of the fraction. Negative 5 equals 4. It's just kind of like math etiquette. However, if you left it in the denominator, right? You have one question for homework in this, and then I'm having it because we have to use the homework stuff for this on. This is it. This is the one question for homework, because most of it uses going to class meeting for later tomorrow. Plus the 5 questions. And I'm going to come around every day and check, did you do the 5 questions? Do I care if they're right? No, and I'm going to give you the answers the next day. I'm not going to give you that now, you can just copy them all and that will waste all of it.